Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Welcome again to this last session about data-driven environmental science. And our first speaker comes from NCSA at Illinois in Chicago. And he's going to talk to us about opportunities for integration of multimodal data and data for the water sciences community.
Well, good afternoon. As the chair just introduced, the title of this presentation is about opportunities for integration of multimodal and data for the water science community. And this is co-authored by David here, who was a postdoc when he worked at NCSA and now is on the faculty member at Rutgers University, and Barbara Minsk, who is a professor at both NCSA and Department of Civil and Environment Engineer. And I worked at NCSA Cyber Environment and Technology Group. And since this session is about data-driven environment science, and NCSA already has several technical talks about our technology, included TuPro this morning and streaming data technology yesterday. So my purpose of this talk is trying to give a perspective from the data-driven environment science perspective on how our technology actually enable things that which were hard to do or not easily to do, and I'll try to explain many challenges and particularly the use case that we are targeted on. So this is the outline of my talk. So in the introduction part, I will basically describe the term of models, because I realize when we talk about models, well, that's basically everybody means different things. So I want to just pinpoint exactly what I mean here, and then two particular problems of interest I want to highlight in this talk is one is the data resolution gap. So how we actually enable multimodal data integration and transformation at runtime. And then the other one is injecting observation data for real-time model calibration. So these two specific problems are motivated by our use case, which I will highlight later. And I also try to put this in a perspective from the community perspective, and try to highlight the community trends on integrating multi-models, and specifically because I have been involved with two initiatives. One is called CSDMS, Community Service Dynamic Modeling System, and then the other one is the Quasi Modeling Framework platform. So I will talk about a little bit on that, and then use case is basically a specific case under the name of real-time data-driven application and system, and in particular we are talking about the stormwater management case, and I talk about some challenges, our results, and some discussion, and finally the conclusions. So in this talk, I basically classify the models into two broad categories. One is the data-driven models, and usually it's some statistical machine learning methods that trying to calculate some kind of meaningful statistic, or trying to fuse the data, or trying to learn something from the data, or maybe just simple filtering and transformation, doing some interpolation or extrapolation. And those are all domain-specific models, but it's purely just data-driven and doesn't involve any physics with it. But then on the other hand, there are a bunch of physics-based models which have been developed in many communities. In the environmental community, that's the same thing. So while people are talking about the data-driven environment science, I think it's important to not forget about the physics-based models, although these two are actually interrelated. So I can give some examples later. So this kind of physics-based model basically describes physics-based differential equations for key physical processes, and for example, hydrology and hydraulics models. And these two kinds of models can be used in a mixed and matched way. And so you could have multiple hybrid data-driven models to process observation data or any particular input data. For example, you could use all kinds of machine learning tools for peak flood forecasting without invoking any particular physics-based model or any particular hydrologic models. But the second case would be that you could have multiple physics-based models and you run for the same kind of scenario, but then at the end, you would use particular data-driven model or several data-driven models to select based on the fitness of the physics models, the input and output, and trying to see, based on that criteria, to select the particular hydrologic models. And then lastly, you could have multiple data-driven models first run against with some kind of observation models, and then you run some physics-based model to basically validate or fuse them to correct bias so that you get better results. So those are all the generic scenarios you would encounter in today's data-driven environmental science. And in particular, I mean, there are many problems with how we can enable that kind of multi-model integration. But in particular, I want to talk about two specific problems. First one is we call the data resolution gap problem. So you have multiple data integration. You want to integrate whether it's data-driven or physics-driven. Usually the data exchange at a specific spatial location or time steps in different models have different spatial temporal resolutions. And for temporal dependency, sometimes you could have a sequential or loop-based relationships among models. So those are basically the biggest challenge, even before we can actually start to say we do all the science-driven decision-making or anything like that. So I will give a specific use case and later to illustrate the point. And the second one is injecting observation data for real-time model calibration. And this is very typical in dynamic data-driven application in a system or adaptive control of environment system where you want to run some model to predict what you need to act. But then at the beginning of your prediction model run, you don't have the real data. But while the action is progressing, you need the real data to calibrate both your input and your actions. So there's a feedback loops there that we need to act upon so that you are not just running models in the pure cyber world without taking into account what's actually happening in the physical world. So that's one the other major challenge. So I want to highlight two specific water science community trends. There are many other smaller ones, but these two I happen to know, so I just highlight here. So the first one is the community service dynamic modeling system. So they are doing integration of simplified OpenMI, which OpenMI I will introduce just next slide, and DOE's common component architecture. And I have been on their cyber informatics and the numerics working group for almost a year, and just trying to learn what they are doing, and so this is I think it's a huge initiative and investment from NSF for a single sub-community in the environment area. And then the other one is more broad, well known, is the Quasi Consortium of Universities for the Advancement of Hydrologic Science Community Hydrologic Modeling Platform. So that's basically an initiative that which creates a blueprint for a community hydrological modeling platform and trying to do things and realize that dream for in the next 5 years. And they are currently considering an Earth System Modeling Framework and OpenMI. And these are two major initiatives, although from my observation right now, mostly they are considering just physics-based model kind of integration. But I will highlight that that's probably not enough for our use case. So in general, why is it often difficult to link models? Of course, it's written in different program languages, but then the biggest thing I see right now when we actually start working on this kind of projects is the data resolution gap. So for example, the physics-based model usually have different dimensionalities, and they may use different types of computational grids, rectangles, triangles, polygons, and each model may have their own time loop or clock. So if you want to integrate them, I mean, that's the first gap you want to solve. And for physics-based models, CSDMS actually summarized in 3 common types of coupling issues. The first one is you have a vertical stack of grids which may present different domains, different subdivision of the domain, or different process in the environment, and you want to layer them together, and then between layer you want to communicate the data. And then the second type is nested. Usually you have a high resolution model embedded in a lower resolution or more larger scale model, and it's sort of like adaptive mesh refinement, but they are in different models. And then the third one is sort of like a boundary condition kind of coupling. You happen to have different models use the same boundary, but then modeling different kind of process, so you have to share that data transfer between that boundary. So this is a picture from CSDMS strategic plan, and basically you can see it said data integration in modeling, but basically it says that you have so many models describe so many processes, and you want to integrate them at boundary, at the initialization part, at the parameter part, and of course you want to present a global view of the results. And that's basically the big chance that people want to do, and of course is not realized yet. And then OpenMI, which is another standard or interface standard that came from Europe, and they have been spent lots of efforts on defining how water models, in particular physics-based model, because that's what they are considering, but they are not considering specifically like the use case I will present later. So, but in general, what they are doing is basically trying to treat the model as linkable component. But since not all models are created equally as component, so you have to wrap it, and then OpenMI provides that kind of interface. And the basic mechanism they use to integrate data is basically request and reply. supervisor, you send a request and you wait and hope you get a reply. And the current version is 1.4, and they said later on they will offer a loop mechanism. The basic command is basically just get values, and you can implement that interface in any program language you want. So the exchange data are described by quantity, time description, or location, which is basically what I call the spatial-temporal thematic information. But since it's a request and reply, and specifically for linking physics-based models, it's not necessary, especially for our real-time case, it's not necessarily useful at this moment. Although I'm in the process to learn how that maybe can use. But as I said, even the CSDMS community, they are basically simplify this and try to integrate with, and use the DOE CCA framework. So back to what we are doing right now. So our use case basically is based on real-time stormwater management system in Chicago. And by the way, this kind of stormwater management system is very common in many urban areas, the urban cities in U.S., all over the world. I mean, in U.S. alone, there are several hundred cities suffer this kind of deficiency in managing stormwater. So what exactly the difficulties here? So as you can see, in a normal dry weather system, you will have a combined sewer system, just transport the sewer from your residence, your business district, and it will be discharged to the wastewater plant, treatment plant. But then when the storm comes, this same system will transport the rainfall, the stormwater, and then when the capacity is exceeded, then there's no way to pump it to the wastewater treatment plant, and then they have just discharged to the river, which cause pollution and many other health issues. So in Chicago in particular, there are multi-billion dollars construction project to construct the underground tunnels and tanks, try to store the stormwater in case they can alleviate this kind of problem. But even after they spend billions of dollars, or in the progress to spending that, there's still a major challenge. Although they have improved a lot, but they still want to know when I can actually transport or redirect the combined sewer to another pipe or another tank, when I can actually open the gate to release the water to minimize the impact. So this is to illustrate the actual complexity here. I want to show you the animation. Let's see. No. Where is the animation? Is it closed? Oh, it's just play. Okay. Right. So as you see, on the right side, there's the lake, Michigan Lake, and on all those network lines is basically the Chicago sewershed. And then the moving clouds, as you can see, is just rain and a rain in progress. And all the red dots is basically the CSO discharge. So as you can see, this happens very fast. I mean, in terms of hours, you would have, this is, I think the animation itself is about 12 hours period, but basically when you actually see the rain front comes, you have to run, if you want to predict how you would act upon this kind of spatiotemporal rainfall feeds on your engineered system, you have to run models, and then you have to adjust what actually happened in the physical world, and then to prevent all those dots happening. So this is a very complex natural engineered coupled system, because the natural part is the weather and rainfall feed, but the engineered system, the sewer network and other things are basically man-made. So in order to tackle this problem, the first challenge we encounter is data resolution gap. So the real-time hydraulics modeling needs real-time rainfall data at spatial temporal resolution that are not readily available anywhere. And so we have to develop data-driven models to transfer real-time raw next-read data into rainfall data and reproduce and republish as new virtual rainfall sensors with provenance as we implement in our workflow system. So we can actually do spatial interpolation, temporal aggregation, and thematic transformation, change rate of refractive to rainfall rate. So as you can see, this big clouds, then you can do arbitrary polygon-based rainfall estimation, and then you get a new real-time virtual rainfall sensors. And when we talk about the virtual sensor, we are not just talking about the new time series data stream, because it's not just numbers of 0.2 2 millimeter rainfall. We have to also manage all those derived metadata, including the spatial location or the polygon areas, the temporal frequency, the thematic interest, and other GIS layers. And that's very, very useful for actually the model, the output actually can be unified, managed with other raw sensor data as well as model, any other model stuff. So the result is we actually can do any real-time, any point real-time based rainfall data. So this was a big cloud here, and then you can see the red point on the map is basically a virtual sensor, and then all those green or white points are USGS gauges. But then we actually can see the model may require a point that are not available in other locations. So we actually can visualize, okay, this is the real rain gauge, those are the virtual rain gauge, and you can tell from the provenance record, and then you can reference details in our paper. And then the other part is the polygon. The polygon is more complicated because this is basically the sewer shed, which is basically each polygon is a discharge unit. So the stormwater will flow to one outfall in that polygon. So by doing polygon-based real-time rainfall data, we can visualize and quantify the rainfall intensity in the whole sewer shed, and identifying which area is the weakest part, and consequently minimally this already gives us the opportunity to improve our situation awareness and understand which part is the weakest link. And this is also has a publication on ACMGIS. Once we have that kind of data, the next step is to do data-driven real-time model predict control. So, as I said, there are in the past when we run models, everything is happening in the computer world. We use computer-generated data and then run a model and then have the output. And you just run once and you say, okay, this is what should be done. But when you actually do real-time model predict control, this is not enough. So what's the challenge? The challenge is that we want to inject in observation data for real-time calibration. So at the beginning of your model run, you want, usually like if you want to predict the next 2 hours, how you're going to react on an unfolding storm, you want to say, I need the rainfall data 2 hours ahead in order to even run this model to predict what I should act upon. But that's a luxury requirement. Of course, we can use some nowcast data from NOAA, but it's a prediction. It's not the real observation data. Once you start running this model, you will see that your predicted rainfall does not match the observed rainfall, which comes continuously from our virtual sensor. And you want to, you also want to see like whether the control action happen in reality matches what you predict that you have to do, but you didn't do that, or you did it in other ways. So there's a feedback loop that you want to recalibrate and infuse your observation data into your input data, so that you can rerun and restart your model for the next prediction stage. So that's the major challenge, and we are actually working on this. Hopefully, have some more results in the future, and I'll just quickly offer some summarization and discussions. So we try to externalize the spatial-temporal semantic metadata management for the model data. So as I pointed out, for both physics-based model or data-driven model, we want to manage those spatial-temporal semantic information, and as well as other metadata. So for example, in the virtual sensor, when you want to actually visualize it, you want to know which GIS layer they are located. And then we feel like at this moment, the OpenMI is not sophisticated enough for us to use for real-time calibration and coupling, and we are working on the adaptive workflow capability. So in conclusion, so the multi-model integration are important for data-driven environment engineer and water science, and our use case basically pose two major challenges. One is the data resolution gap, real-time feedback calibration, injecting data into model at runtime, and we have made big progress on solving the problems, and our ongoing effort will benefit many other dynamic data-driven multi-model application in the system. So, of course, any interest on collaboration will be welcome. And finally, I would acknowledge my founding support and the team in NCSA, which is the Cyber Environment and Technology Group. Thank you.